My name is Hannah, and I'm going to discuss stereochemistry. Stereochemistry is the study of three-dimensional arrangements of atoms and molecules. I'm going to focus on isomers. Isomers are compounds that are not the same but do share the same molecular formula. Constitutional isomers have different atomic orders. They do not have the same bonding arrangements. One of the main focuses of our class has been on stereoisomers, which are the same chemical formulas with a different arrangement in space. On the right-hand side, you can see different isomers comparing C6 with H12 versus C3H6O2. Here is an example of constitutional isomers or structural isomers. These are compounds that have a different order in which the components are bonded. Each of these molecules have 4 carbons but vary in their arrangement. The different type of stereoisomers are geometric, conformational, and asymmetric isomers. Geometric isomers have different chemical formula arrangements across a pi bond, also known as cis or trans. Conformational isomers are molecules that can be made identical with the rotation of a sigma bond. And asymmetric isomers have a sp3 hybridized carbon with 4 different groups on it. This is an example of a geometric isomer. The cis isomer is happening on the same side of the pi bond, where the trans isomer is happening on the opposite sides of the pi bond. This is an example of a conformational isomer. They result from the rotation around a single bond. One of the isomers we have spent the most time on is the asymmetric isomer. They deal with the rotation happening at the sp3 hybridized carbon. They can rotate in a R or S fashion. Depending on the rotation, will help identify them as enantiomers or diastereomers. Enantiomers are mirror images that cannot be superimposed on one another. They have at least one chiral center with opposite configurations. The example given in lecture was your right and left hand. Diastereomers are not identical or mirror images of one another. Diastereomers will have opposite chiral centers, but not all of them will be opposite, whereas the enantiomers will have opposites at every chiral center to give them that mirror image. Other presentations will have more details on each of these topics, where I was just a broad overview of each of the isomers. The main takeaway from my presentation is that isomer relationships describe how molecules with the same molecular formula can be structurally different. Here is my list of references.